This is part 2 of the fall 2013 AP Physics course test exam 8. Here we have a problem 18, a 5 by 10 to the minus 2 kilogram or 50 gram block attached to a spring shown as traveling to the left at 3.5 meters per second when the spring is compressed by 0.1 meters. So x is 0.1 meter negative if I'm defining this to be x and y. The graph shows the relationship between the force applied to the spring and its compression. Well, the reason for needing the graph is they didn't give me the spring constant, so I'm going to have to get that. The spring constant is the slope off the force compression graph because F is kx. So there's the slope. So I'm looking for that right here in order to find the slope, and I see that it takes a 1 Newton force to compress this spring 0.4 meters, in other words 40 centimeters. What is the spring constant? Well, that's the slope. So the spring constant is 1.0 newtons over 0.4 meters. And if I do that right, I believe that's 2.5 newtons per meter. So that's the answer to the first question that's asked. Now we go to the next question. What is the work done on the spring as the spring is compressed from 0.1 meters to 0.4 meters? Well, a spring is a conservative force, so the work done by it is minus the change in the potential energy of the spring. By definition of potential energy, is what defines it. So this is minus the spring potential's final plus the spring potential's initial kinetic potential energy. Now we know that the spring potential's formula is 1/2 k x squared. So the work of the spring is minus 1/2 times k times x final squared plus 1/2 k x initial squared. We can factor the 1/2 and the k, 2.5 newtons per meter out front. The final says that it's 0.4 meters squared, and that's a minus, lost my minus sign right there, plus 0.1 meters squared when it was at its initial position. I plug all that up in it and I find that minus 0.188 joules. Now I want to stop and of course think about it. Does this make sense? The spring is getting compressed, and as it compresses, it applies a greater and greater force in the opposite direction to which this thing is moving. So you've got it like this, and later it's like this. So the object had a displacement this way, and the force was in the opposite direction. So the force is slowing the block down, so that's doing negative work. So yes, I didn't lose any minus signs in the process. Always like to check my work to see if it makes physical sense. What is the block speed when the spring is compressed 0.4 meters? Well, you've got a block, and the block has the normal force acting on it, maybe. It has weight acting on it, and it has the spring force acting on it like this. And it has a displacement in that direction. So the net work, which is equal to the work by the normal plus the work by weight plus the work by the spring, has to equal the change in the kinetic energy. This is the work energy theorem. But there is no work by gravity, it's perpendicular displacement, and there is no work by the normal. So the work by the spring is simply equal to the change in kinetic energy, and we found the work by the spring in part B. So this means this is 1/2 mv final squared minus 1/2 mv initial squared. 1/2 mass times the final speed squared is therefore equal to the work of the spring plus 1/2 mass times the initial speed squared. I can divide by m and multiply by 2. If I do that, I get 2 times the work of the spring over m plus the initial speed squared. So my final speed is the square root of 2 times the work of the spring divided by the mass plus the initial speed squared. Plug in our numbers. I have 2 times minus 0.188 joules divided by the mass of the spring. I have to go find what that was. Let's see, that's 0.05 kilograms. Plus the initial speed. The initial speed was 3.5 meters per second. I need to square that. Plug all that up in. Of course, it's going slower, so the spring is doing negative work, so it's going to be less than 3.5. And when I punched it, I found it was 2.17 meters per second. And that finishes that problem. Alright, the next problem is a problem that is similar to one that I worked in class and in the videos. Susan applies a 15 Newton horizontal force to push a 1.75 kilogram block a distance 2.75 meters up a frictionless incline with an angle of inclination of 30 degrees. How much work does Susan do in moving the block? Well, good to draw a little diagram like this. There's Susan pushing 15 newtons. The displacement is this away. Delta R happens to be equal to 2.75 meters. And this angle there is 30 degrees. So it's easiest just to use the dot product for this. Force dotted into displacement, which is F times delta R times the cosine of theta. The work is 15 newtons, 2.75 meters, cosine 30 degrees. And you punch all that in and you find 35.7 joules. Susan does positive work. She's making the block speed up. Part B, how much work does gravity do on the block? Now, to calculate work of gravity, gravity is a conservative force, so I want to use potential energy to calculate that because that's the easiest way. So the work by gravity is minus delta UG, the change in the potential energy of gravity. This is minus UGF plus UGI. Well, this is equal to minus MGY final plus MGY initial. So the work by gravity is equal to minus mg y final minus y initial minus mg delta y. So I need to figure out how far delta y is. Now, I'm going to push this block up this far. Let's call that distance that we said earlier. So I'm going to push it from, let me highlight correctly, from wherever I'm going to go. If I go from here to there, and that delta R is 2.75 meters. But I also say, hey, look, I know this. There's a triangle here. This is 30 degrees. And this is delta y, which most people generally call h. So to find this side, I need to use the trig function, the sine, times delta r. So I go back down here. And I have work of gravity is minus mg delta r sine of theta. Put in my numbers, minus 1.75 kilograms, 9.8 meters per second squared, 2.75 meters, and the sine of 30, which is a half. And punch all that in, and I get minus 23.6 joules. Gravity is attempting to slow the block. How much work does the inclined plane? Well, the inclined plane's normal force is perpendicular to delta r. So the work by the normal is 0. It has no component along the direction of the displacement. And that finishes problem number 19. With that, we'll actually see you in the next video.